Welcome back. In example 3, we're asked to find the volume of the solid generated by revolving the region between the y-axis and the curve x equals 2 over y, where y goes from 1 to 4, about the y-axis. And figure 20 shows a little picture of what's going on here. But I want to point out the key words that you're going to be looking for with these examples. One of the key things that sticks out to me is that we're revolving the region about the y-axis. So that revolving is going to tell us something about what the cross sections are. What kind of cross sections are we going to be looking at here? If you said circular cross sections or discs or something like that, then that's correct. This is in contrast to example 2, where we were told exactly what the cross sections were. In that case, we had isosceles right triangles. But here, we're told that we're generating this solid by revolving a region about an axis, and that process of revolving is what's going to make these circular kind of cross sections. All right, one other thing I wanted to point out was this curve, x equals 2 over y. That may seem a little bit unfamiliar, like you may get a little bit uncomfortable when you see x equals a function of y. But remember, if you want to get a feel for what these things look like, you can always solve these equations for y. Well, maybe not always, but a lot of times you can solve these equations for y in terms of x. So we could take like the y variable, multiply it to the right, to the left, and then divide the x variable to the right. So we have 2 over x. And that starts to look a little bit more familiar. That's like our y equals 1 over x function, but stretched vertically by a factor of 2. So that's the one that's going to fall as you go to the right in the first quadrant. That's what we're seeing right here. Now, of course, we have some other constraints on our region. It's not just that falling curve as you go to the right. We have y is going to be going from 1 to 4. So from 1 to 4. So we have our little interval set up in y. And we're going to take this region then and and the y-axis is also one of our boundaries of our region. So that pretty much cuts off this region right here that's shown in figure 20. So we're going to take this region and revolve it about the y-axis. Let's draw that little symbol to remind us which axis we're revolving about. Okay, well, here our cross section is going to look like some kind of circle or a disc. Let me just draw a little sample cross section. So it looks something like this circle here. And in fact, I'm going to take this immediately and plop it in a 2D setting, like plop it flat on the page. So here's our circle, circular cross section. Now, the thing about this is, just like before, we want to figure out what the radius of this circle is. But the radius here is really going to depend on what the y value is here. It's different from example 1, where we had our region kind of along the x-axis. Now we have our region along the y-axis. And not only that, but we're revolving about the y-axis. So when we try to find our cross sections that are going to be circles, they're going to be horizontal cross sections. They're going to be perpendicular to the y-axis. Generally speaking, the cross sections that you're going to get from revolving a region about an axis, the cross sections that are going to be circular are going to be the ones that are perpendicular to the axis of rotation. So perpendicular to the y-axis in this case. So we're dealing with a different kind of cross-section here, a horizontal cross-section as opposed to a vertical cross-section. And you're going to get one of these horizontal cross-sections for each y value as you go from y equals 1 to y equals 4, as you go across your solid. So it looks like our approximating units are going to be in terms of y. They kind of depend on y here, not on x. So we're going to want to figure out what the radius of this circular cross-section is as a function of y rather than x. So what is that radius right there as a function of y? So if we're looking at the cross-section at a y value of just y, then what would a formula be to get the radius of that circular cross-section? So if you said that's going to be 2 over y, then that's correct. This will be 2 over y. You can think take this x value over here on this curve, which is given by x equals 2 over y, and then look at the distance between that x value and this x value over here at the center of these circles, which is just x equals 0. And when you subtract them, you just get 2 over y minus 0, so the right x value minus the left x value, and that gives you that horizontal distance right there, which is what the radius is. So it's going to be 2 over y for the radius of each of these circles. You can check that too. Like imagine your y value were 1, right? If you had a y value of 1, then you'd have some kind of circle like this, and the radius here looks like from the picture is going to be 2, but if we use our formula, we can also get that. We take our x equals our 2 over y formula for our radius, and we get 2 over 1, which is 2. So it checks out, at least with that edge case there. Okay, so we have the radius of each of our cross-sectional circles, and so now we can get the area of each of those circles or disks. This is going to be a function of y. We're going to get a different area for each value of y as y goes from 1 all the way up to y equals 4. So remember, the area of these circles are going to be pi times the radius squared, which is pi times 2 over y squared. Or you can write 4 pi over y squared. Okay, now the same exact concept for dealing with cross-sections along the x direction applies to cross-sections along the y direction. If you want to find the volume of the solid that's generated by all these these circular cross-sections, you're going to integrate all those areas. But everything's just in terms of y. If you think back to how we were using approximating cylinders, well, if our cylinders are horizontal, then the radius of these cylinders is going to be some kind of function of y. It'll be different depending on which y value you're at. And the width of each of those cylinders would be a delta y, right? It'd be like a little distance in the y direction. The subintervals here are little lengths in the y direction. So everything's just in terms of y. It's all along the y direction here. So those delta y's turn into dy, and the approximating areas turn into the true areas as a function of y, or approximating volumes, I should say, turn into the true volumes. And so what we have is the integral from what to what here. So if you said y equals 1 to y equals 4, that would be correct. We're no longer integrating across the x direction. It's not going to be x equals 0 to x equals 2. Now everything's in terms of y. We're going from y equals 1 up to y equals 4. That goes across our solid. Okay, so we're going to plop in our, I don't know why I'm using plop all the time. Try to come up with a different word. We'll gently place our area of cross sections into our integral with love and care. And then I better find the antiderivative here. Remember, so this is one of the things I wanted to bring up. Remember that if you have a y squared on the bottom, when you're finding the integrals, you can rewrite that as y to the negative 2, right? So bring the bottom of your fraction up to the top, just so that you can use that reverse power rule of adding 1 to the exponent and then dividing by that new exponent. And here I've taken the 4 pi constant out of the integral, out in front, just to set it aside. So our antiderivative would be y to the negative 1 over negative 1 from y equals 1 to y equals 4. I could clean that up a little bit and write this is like negative 1 over y from 1 to 4. Right? Dividing by negative 1 is the same thing as multiplying by negative 1, so you get negative y to the negative 1, so that's negative 1 over y. Then I can go ahead and plug in the 4, put a minus, plug in the 1, and inside here you're going to get 3/4. So one of the 4's will cancel, and you'll get a 3 pi left. And if there's anything better than 1 pi, it's 3 pi. This is actually really interesting, though. Like the volume of that solid that's generated by rotating this region about the y-axis turns out to be something simple like 3 pi. It's really pretty amazing, considering all the little variations of the shape as you're scanning across that solid. Okay, but enough of that. Thank you so much for watching this part. We'll tackle example 4 in the next part.